One concern I have in this chapter is that there's a lot of specific terms, and many of them are great to know and are an important part of our vocabulary when we're using them. But we can often keep as crude as accuracy and precision while still having the ability to recognize the differences. So I want to be a little bit careful not to get too in the weeds, and this is about as far as I want to go on some of the subtleties of when we can detect a substance. But that said, there are two important concepts that are really hiding here. Now, our limit of detection, this top part, when can we see that we're not at zero anymore? Now think through exactly what that's going to look like for a second. If we have our typical axes, we're going to try to do some sort of a calibration curve. When do we actually have the ability to say that with the error bars, this point is no longer zero? Well, for that we're going to have to take our error bar. We have to have some sort of a notion of when the error bar is now officially small enough that we can say, yep, we've exceeded zero. That's going to be called the signal detection limit. And our rule of thumb for that, you're going to take your blank and you're going to look at the signal that you're getting from that. The book calls it Y. I'm going to call it signal, just to kind of get us thinking about the fact that this is always what we're measuring. And sometimes we take that signal through a couple of more steps to get what we actually plot, but we're actually focusing on the signal itself coming off. So we take our blank signal. So in other words, we put a sample on that has none of our analyte. We see how much background noise we've got. We're going to add 3 standard deviations to that. Now notice that that doesn't mean that we know anything at all about the concentration, because what we're saying is that when I stick water on here, the randomness of it jittering around gives me this much noise. And occasionally I'll see a spike that's getting off of zero. Let me just give you another example of that. Suppose you're sitting there looking at the digital display on some instrument. Maybe it's a Spec 20, or maybe it's the analytical balance. You're standing there looking at you've zeroed it out. You're watching it. Watch it for about 2 minutes. Do you ever see the number leave zero? Sure, almost definitely. And that means there's just a tiny bit of randomness, and it's causing it to occasionally flicker. Now, when you see the analytical balance go from 0.0000 to 0.0001, do you actually believe that there's that 1/10 of a milligram sitting on the balance that just happened to land and fall back off? No, of course not. You think, okay, that's just some random noise. Which means that you really can't believe it at all if you see that it suddenly turns solid and starts telling you that it's 0.0001 milligram. You just aren't going to believe that yet, because you've seen it fluctuating, and so you know this could just be randomness and this could be a tiny bit of drift, though drift is something separate. The key part is we can start to say, based on that standard deviation, if we see that the standard deviation on our balance is maybe 0.0001, when it says to say 0.0003, and it keeps it there steady, we might start to believe that, yep, that's not zero anymore. But are you really confident that it's exactly 0.0003 grams? No. You're still kind of like, all right, it's not zero anymore, but I don't quite trust the number. That's limit of detection. Okay, then the book's going to point out that, and rightly so, that was our signal limit of detection. There's an equation in the book that doesn't necessarily highlight this. If you divide 3 standard deviations by the slope, this spot is going to actually tell you the minimum concentration that you can detect. And so that would actually be your detection limit. So your minimum detectable concentration is going to be wherever you got your signal detection limit, just on the x-axis. Now just because you can see it doesn't mean you can actually claim that you really know how much is there. And that's really the goal in analytical chemistry most of the time. Now, for that we're actually going to have something we call the lower limit of quantification. I'm just going to abbreviate that, lower limit of quant. Now, by definition, that's going to be, in fact, let me use the definition symbol. There we are, the three-lined equal sign. We've defined that to say that it's going to be 10 standard deviations. Oops, it's supposed to be an S, 10s, divided by our slope. Up here for our detection limit, that was 3s divided by slope. So you can see what we've done is we've gone 3 times higher, roughly, before we actually believe the number well enough to start telling somebody, oh yeah, I totally believe that this is the real concentration. Now here's the reason why. Our blank, this had a standard deviation associated with it. Our measurement had a standard deviation associated with it. We need to get these separate enough that we don't actually believe that there's any realistic overlap between them, and that it's even worth talking about things. Now, you could just try to go to the spot where they barely overlap, maybe like 3 standard deviations, 3 standard deviations. So maybe you say 6 standard deviations away would be good enough, but they defined it to be 10 instead, so that you actually start having a little bit of range between them. Because you're really just at the edge of saying, yeah, well, 3 standard deviations away, I'm still only at 99.9% confidence, so, one time out of 1,000, it's still going to randomly be that far out. One time out of, well, I'm probably going to do the combination wrong here. One time out of 2,000, you can have these two bump up to each other. I honestly forgot that part of stats a little bit. Exactly how you entangle 2 separate standard deviations. I'm not sure that it's a linear addition like that. But still, you get the idea well enough to say, okay, I get it. You're saying that if I flip a coin 1,000 times, yeah, finally I've done it on this side. The other guy has done it too. That's what we're talking about for those two. Well, we want to make sure they're separate enough that there's some ability to define exactly where it is between them. Because if it's this Gaussian, it's kind of bleeding between the two. And so if we're in the middle, we wouldn't be able to say with confidence that it's not only separate from this, but it's not up there yet either. So in order to have that distinction, we defined the lower limit of quantification to be 10 standard deviations times the slope. So that's going to be the smallest concentration that you're able to actually claim to see.